Hello everyone, this is Xiang, a senior software engineer from Google. Today I'm going to talk about our recent work on super resolving commercial satellite imagery using realistic training data. This is a joint project between Google Maps and Google Research. Let's first look at some image examples from Google Maps. They are all labeled as satellite view in Google Maps, and apparently their resolutions are different. The first one on the left is from a US city, and it has a very high resolution. The road marks are sharp, and we can see many details of the vehicles, such as side mirrors, sunroofs, etc. The second one in the middle is from Taipei, and it has a moderate resolution. The road marks are visible with some blur. We can easily identify the vehicles, but with little detail. The third one has the lowest resolution among the three. The crosswalks are completely blurry. In fact, I cannot even tell whether the black blocks are vehicles if they are not located on the road. The reason for the resolution difference is because they are from different sources. The first one is in fact taken by an aerial imagery system owned by Google. Its resolution is less than 10 centimeters per pixel, and we can only get such high-quality images in the countries where Google is allowed to take aerial images, like the US. For the other places, we have to rely on real satellite images. The second one is of the highest resolution we can get from commercial satellite imagery market, which is about 30 centimeters per pixel, and they are relatively expensive. The third one is cheaper, and it is about 50 centimeters per pixel. Now the question is, given a relatively low resolution satellite image, can we improve it via single image super resolution methods? We know there are a lot of convolutional neural network based super resolution algorithms proposed in the recent years. People generate synthetic low-res and high-res image pairs via a degradation model and send the image pairs into the network training process so that the network can learn how to transfer a low-resolution image to its high-resolution version. Most of the existing algorithms use a simple image degradation model, while high-res image Z is convolved by an invariant point spread function h, followed by a downsampling operation. The shape of the point spread function is isotropic, and usually people just use a Gaussian-shaped model. Some papers make the model more realistic by adding a wide Gaussian noise term. They use this model to generate training image pairs, and the trained network is then applied to various images, including those taken by your cell phones, SLR cameras, and of course, some of them have been applied to satellite images. The question is this training data generation model good enough for the commercial satellite images? We did some research. This is a sample image from the GLI-1 satellite. We took two small patches and estimated their point spread functions. It turns out that, first of all, the point spread functions are not isotropic. They are directional, which means there is probably some mild motion blur, and the motion direction slightly varies over the space. The satellite images can also be noisy, like this example. which is from the Pleiad satellite. We extracted the noise and applied a DFT. We can see this is not white Gaussian, but it can be synthesized by convolving white Gaussian noise with a kernel. Here are some conclusions from our analysis. First of all, the satellite image's optical point spread functions are spatially variant within and across images. However, it varies slowly over the space, so that locally it can be treated as invariant. And they may not be isotropic, since there could be some mild motion blur. Secondly, according to some documents from the image providers, commercial satellite imagery products are not in the native sensor coordinate system. They are resampled in order to align with their pose model, which can explain the kernel we found from the noise. That could be a resampling kernel. So, a realistic degradation model should be like this. Compared with the previous model, this one contains 2 point spread functions, a spatially varying optical point spread function HO, and an invariant resampling kernel HP. It also has a resampling operation. And this model can be further approximated by a simpler model. While the latent high-res image Z is in the resampled coordinate system. It is convolved by a spatially varying kernel HM that includes both HO and HP in the above model. The image then gets downsampled and a colored Gaussian noise is added. We use this model to generate training image pairs. Aerial images are selected as the data source instead of satellite images in order to avoid noise and motion blur in the target high-res images. The point spread functions are simulated via an elliptical Gaussian mixture model, which is invariant inside a single training image, but changing across images. Noise is synthesized using the way we described earlier. We developed a neural network based on an existing paper showing in the slide. We also improved its performance by adding a pseudo-Hilbert loss and a machine learning-based perceptual term to the overall loss function. Here are the super resolution results from synthetic low-resolution images. You can see that the neural network is able to handle varying point spread functions. We then applied it to real 50 cm GOI-1 satellite images with upscaling factor 2x. We compared it with the results using the traditional training data generation model that uses a fixed Gaussian point spread function and white Gaussian noise. The neural network is the same, and we can see the proposed training data generation model outperforms the traditional one in all the examples here, which means the proposed model is more realistic. To quantitatively measure the proposed model's performance, we super-resolved over 1,000 real satellite images using different methods and sent them to ordinary viewers to collect their opinion scores. The results confirm that the proposed model significantly improves visual image quality. Let's look at more real examples. This is a 50 cm GOI-1 image. Let's look at some details here. We super-resolved it onto a 30 cm image grid, where you can see the improvements. Let's go back and forth. Before super-res, after super-res. Before super-res, after super-res. We compare it with the real 30 cm World View 3 image in the same area. Though there are some seasonal changes, we can still see that the super resolved image's quality is comparable to the real one. In fact, it looks even sharper than a real 30 centimeter image. Super resolved 1, real 1. Super resolved 1, real 1. This is another example. This is the original 50 centimeter GOI1 image, super resolved onto 30 centimeter image grid. Before super res, after super res. Before super res, after super res. And compare it with the real 30 centimeter world view 3 image in the same area. Super resolved 1, real 1. Super resolved 1, real 1. One more example. Before super res, after super res. Before super res, after super res. So you can see that by using this technology, we can probably buy cheaper 50 centimeter images instead of the 30 centimeter ones and save some money. But maybe that's not a good idea. We can still buy 30 centimeter satellite images and apply the proposed technology to get aerial image resolution. Here are some examples. This is a 30 centimeter world view 3 image before super resolution. This is the one super resolved onto 15 centimeter image grid. Before super res, after super res. Before super res, after super res. One more example. Before super res, after super res. Before super res, after super res. And that ends my talk. Thank you for the time.